June 23, 1942. The captured American vehicle sat beneath a canvas awning outside Tobruk, its hood propped open, radiator still warm from 3 hours of continuous operation across soft sand in temperatures exceeding 45 degrees Celsius. Oberst Friedrich Weber, a mechanical engineer from Stuttgart who had designed cooling systems for Daimler-Benz before the war, circled the jeep with the methodical precision of a surgeon, examining an impossible patient. His field notebook, later discovered in German military archives, contained a single line written that evening that captured his professional bewilderment. The American cooling system operates on principles that our engineers insisted would fail catastrophically in desert conditions. Yet, after sustained maximum throttle operation in conditions that destroyed 3 Kubelwagen engines this week, the water temperature remained stable. We have been taught that American engineering emphasizes mass production over quality. This machine proves otherwise. Through 18 months of brutal desert warfare, Wehrmacht mechanics watched their carefully engineered air-cooled Kubelwagen engines seize from thermal overload, while captured American jeeps performed with maddening reliability in conditions German doctrine declared impossible. Water-cooled systems. The radiators should have boiled over. The engines should have cracked cylinder heads. The cooling fans should have failed under the constant assault of fine desert sand. Instead, the jeeps simply kept running, hour after hour, day after day, through conditions that turned the North African campaign into a mechanical graveyard for German vehicles. This disparity would force one of the most comprehensive technical evaluations in Wehrmacht history, conducted by engineers trained to believe in German technological superiority, now confronting undeniable evidence that American engineers had solved problems German doctrine claimed were unsolvable. The revelation began on May 12, 1942, when elements of the 21st Panzer Division captured their first intact American jeep near Gazala. British forces had been using jeeps under Lend-Lease since late 1941, but this was the Wehrmacht's first opportunity to examine the vehicle's mechanical systems closely. Hauptmann Otto Steinmetz, who supervised the initial technical inspection, noted in his report that the captured vehicle showed approximately 15,000 kilometers on the odometer and clear evidence of hard desert use. Yet when German mechanics started the engine and brought it up to operating temperature, the cooling system functioned flawlessly. The radiator pressure remained stable. The coolant circulated properly. The temperature gauge settled at normal operating range and stayed there. For engineers trained in German automotive theory, this should have been impossible. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. German military doctrine regarding vehicle cooling systems in 1942 reflected years of careful engineering analysis and field experience. The Wehrmacht's standard light reconnaissance vehicle, the Volkswagen Type 82 Kubelwagen, employed an air-cooled engine specifically because water cooling systems were considered fundamentally unsuitable for desert operations. This wasn't arbitrary prejudice, but reasoned engineering judgment supported by extensive testing. Water-cooled engines required radiators that were vulnerable to combat damage, cooling fans that consumed power and created mechanical complexity, water supplies that might not be available in desert conditions, and coolant that expanded when heated, creating pressure that could rupture hoses and crack engine blocks. The Kubelwagen's 985 cubic centimeter air-cooled flat-4 engine eliminated all these vulnerabilities. Cooling fins machined into the cylinders dissipated heat directly to the air. A belt-driven fan forced air across the engine. No radiator meant no coolant to leak, no water to boil over, and no vulnerable plumbing to fail. This represented sophisticated German engineering, elegant in its simplicity and theoretically superior to the American approach. Yet, by mid-1942, Wehrmacht mechanics working in North Africa were observing a disturbing pattern. Kubelwagen engines, despite their theoretically superior air-cooling design, were failing with alarming frequency under sustained desert operations. Feldwebel Hans Kruger, a master mechanic who managed vehicle maintenance for the 10th Panzer Regiment, documented the problem in monthly reports sent to the Army Weapons Office in Berlin. His June 1942 report detailed specific failure modes that contradicted the theoretical advantages of air cooling. During sustained high speed operations across soft sand, when engines operated at maximum RPM for extended periods, the air cooling system proved inadequate. Cylinder head temperatures exceeded design limits. Oil began breaking down, losing its lubricating properties. In extreme cases, pistons seized in their cylinders, destroying engines that required weeks or months to replace. The problem wasn't design deficiency, but operational reality. The Kübelwagen's 25-horsepower engine, already marginal for desert conditions, had to operate constantly at near maximum output. This sustained high-load operation generated more heat than the air cooling system could dissipate, especially when vehicles travelled slowly through soft sand where minimal airflow reached the engine compartment. By contrast, captured American Jeeps seemed immune to thermal problems. The Willys MB's Go Devil engine, a 134 cubic-inch inline four-cylinder unit producing 60 horsepower, employed conventional water cooling with a pressurized radiator system. German engineers examining captured Jeeps expected this cooling system to fail quickly under desert conditions. The reasoning seemed sound. Fine desert sand would clog the radiator, blocking airflow and preventing heat dissipation. Coolant would boil in the intense heat, creating steam pressure that would blow gaskets or crack the engine block. The water pump, operating in contaminated coolant filled with sand and minerals, would fail, stopping circulation and causing immediate engine seizure. Rubber hoses, degraded by heat and ultraviolet radiation, would split or burst, dumping coolant and destroying the engine. None of this happened. The Jeeps kept running. Hauptmann Weber's examination of the captured Jeep in June 1942 represented the first systematic German attempt to understand why. The vehicle was transported to an improvised testing facility near Tobruk, where German mechanics could conduct controlled evaluations. Weber, whose pre-war work at Daimler-Benz included cooling system design for both air-cooled and water-cooled engines, approached the examination with professional skepticism mixed with genuine curiosity. His background gave him expertise to recognize engineering excellence when he encountered it, even in an enemy vehicle. The testing began with basic measurements and documentation. German technicians photographed every component of the cooling system. They measured the radiator's dimensions, counted the cooling fins, documented the fan's diameter and pitch, examined the water pump's construction, traced every hose and fitting, and recorded the thermostat's operating temperature. What they discovered challenged fundamental assumptions about water cooling in desert conditions. The radiator itself was larger than German theory suggested necessary. It measured approximately 16 inches tall by 20 inches wide, with a core depth of about 2 inches. The cooling surface area substantially exceeded what German calculations indicated for a 60-horsepower engine operating under normal conditions. This oversized radiator represented American engineering philosophy, generous margins rather than optimized minimalism. Where German engineers calculated exact cooling requirements and designed systems to match those specifications precisely, American engineers apparently calculated requirements and then added substantial capacity beyond what calculations indicated was necessary. This approach seemed wasteful to German technical thinking, but it provided immunity to the unexpected thermal loads that destroyed more precisely optimized systems. The radiator surge tank particularly intrigued Weber. This brass reservoir, mounted high on the vehicle near the radiator, served as an expansion chamber for heated coolant. As coolant temperature increased and volume expanded, excess liquid flowed into the surge tank rather than forcing its way past gaskets or blowing off through the Pfeffer radiator cap. When the engine cooled and coolant contracted, the surge tank supplied liquid back to the radiator, maintaining proper fill level. This simple device solved one of the fundamental problems that plagued water-cooled engines in desert conditions. Without the surge tank, thermal expansion forced coolant out of the system, leading to gradual coolant loss and eventual overheating. With the surge tank, the system was self-compensating. Coolant that expanded out of the radiator during hot operation returned when temperatures dropped, keeping the system properly filled indefinitely. German engineers examining the surge tank recognized its elegant simplicity. The component added minimal weight, required no maintenance, and solved a persistent problem. Yet, German cooling system designs in 1942 did not incorporate surge tanks. The oversight seemed glaring once the American solution was demonstrated. The cooling fan drew particular attention from German mechanics. American Jeeps used a 4-blade steel fan, approximately 14 inches in diameter, mounted directly on the water pump shaft. The fan drew air through the radiator whenever the engine ran, providing consistent cooling even when the vehicle moved slowly or stood still with the engine idling. This contrasted with German practice of using belt-driven fans whose speed varied with engine RPM, sometimes providing insufficient cooling at idle or excessive parasitic drag at high RPM. The Jeep's fan was fixed speed, providing adequate cooling across all operating conditions. German mechanics tested the cooling system under conditions designed to reveal its limitations. They operated the Jeep at maximum throttle while stationary, simulating the worst-case scenario of maximum heat generation with minimum airflow through the radiator. German theory predicted the engine would overheat within minutes. Instead, the temperature gauge climbed to normal operating range and stabilized. The cooling system maintained equilibrium, even under conditions that would destroy most European engines. They drove the Jeep through soft sand at sustained high speed, loading the engine heavily. The temperature remained stable. They operated the engine for hours, at maximum load in ambient temperatures exceeding 45 degrees Celsius. The cooling system continued functioning normally. Weber's technical report, submitted to the Army Weapons Office in July 1942, contained conclusions that contradicted German assumptions about cooling system design for desert operations. The American water-cooled system demonstrates superior heat dissipation capacity compared to the Kübelwagen's air cooling. The generous radiator size, combined with the surge tank's ability to compensate for thermal expansion, creates a system resistant to the thermal cycling that destroys more precisely optimized designs. Most significantly, the American approach accepts weight and complexity penalties to achieve reliability margins our own designs lack. Under laboratory conditions, German air cooling offers advantages. Under combat conditions in North Africa, American water cooling proves superior. This represented a profound admission from a German engineer trained to believe in the superiority of German technical solutions. The cooling system's resistance to sand contamination particularly puzzled German observers. Fine desert sand was the enemy of all mechanical systems in North Africa. It infiltrated everything, abrading surfaces, clogging passages, and destroying precision-machined components. German engineers expected the Jeep's radiator to clog with sand, choking off airflow and causing rapid overheating. Field experience proved otherwise. Captured Jeeps that had operated for months in desert conditions showed remarkably clean radiators. The cooling fins remained largely unobstructed. Airflow passages stayed open. Sand that entered the radiator seemed to pass through without accumulating. Stabsfeld-Weibel Kurt Hartmann, a maintenance specialist who supervised Jeep evaluations, investigated this phenomenon systematically. He deliberately drove captured Jeeps through dust storms and across loose sand, conditions guaranteed to fill the air with abrasive particles. After sustained operation in these conditions, he examined the radiators, expecting to find them clogged. Instead, they remained functional. The explanation, once German mechanics understood it, revealed another aspect of American design philosophy. The radiator's cooling fins were spaced relatively far apart compared to German practice. This wider spacing sacrificed some cooling efficiency under optimal conditions but prevented sand accumulation. Fine particles that entered the radiator could pass through without wedging between closely spaced fins. Additionally, the airflow velocity through the radiator was sufficient to carry sand particles completely through rather than allowing them to settle or accumulate. German radiator designs typically used more closely spaced fins to maximize cooling surface area, achieving better heat transfer under clean conditions, but creating spaces where sand could lodge and block airflow. The American design traded maximum theoretical efficiency for practical reliability in contaminated environments. Once again, German engineers confronted evidence that American engineering emphasized real-world performance over theoretical optimization. The water pump's durability surprised Wehrmacht mechanics accustomed to pump failures in desert conditions. Water pumps are vulnerable components, featuring shaft seals that can leak, bearings that can fail, and impellers that can corrode or erode. German engineers expected captured Jeep water pumps to fail rapidly when operating with coolant contaminated by sand and minerals. Field experience contradicted this expectation. Jeeps captured with 10,000 or more kilometers on their odometers typically had original water pumps still functioning normally. Obergefreiter Wilhelm Becker, a machinist from Essen who specialized in pump repair, disassembled multiple Jeep water pumps to understand their construction. His technical analysis, preserved in Wehrmacht maintenance records, documented the pump's robust design. The pump housing was cast iron, resistant to corrosion and erosion. The impeller was bronze, a material that resisted both corrosion and wear from abrasive particles. The shaft seal was a simple packed gland design, less sophisticated than German spring-loaded seals but more tolerant of contaminated coolant. Bearings were oversized for the application, providing service life margins that prevented premature failure. The entire assembly could be disassembled and rebuilt using basic tools, enabling field maintenance that kept pumps operational indefinitely. Becker's report noted that while German water pump designs were more elegant and efficient under ideal conditions, the American pump was more forgiving of harsh operating environments and poor maintenance. This robustness, through simplicity and generous engineering margins, proved more valuable than German precision and optimization in desert combat conditions. The thermostat's operation also differed from German practice in ways that improved desert reliability. The Jeep used a wax pellet-type thermostat that opened gradually as coolant temperature increased, allowing precise control of engine operating temperature. German engines typically used thermostats that opened more abruptly or, in some cases, no thermostat at all, relying on coolant circulation determined by pump speed alone. The gradually opening thermostat meant the Jeep's engine reached operating temperature quickly, reducing wear during cold starts, then maintained optimal temperature across varying loads and ambient conditions. This precise temperature control prevented the thermal shocking that could crack engine blocks or cylinder heads when cold coolant suddenly mixed with overheated coolant. German mechanics testing captured Jeeps noted that engine operating temperature remained remarkably stable, regardless of operating conditions. Whether idling in shade or climbing sandy slopes at maximum power, the temperature gauge stayed within a narrow range. This stability reduced thermal stress on engine components, contributing to the remarkable durability American engines demonstrated in desert service. By autumn 1942, German forces in North Africa had captured approximately 40 Jeeps in various conditions. Many were immediately pressed into service by capturing units, but 6 were sent to Germany for comprehensive evaluation at the Army Weapons Office testing facility near Berlin. These vehicles, accompanied by detailed reports from Afrika Korps engineers, arrived in late January 1943. The testing in Germany represented the most thorough technical analysis any captured Allied vehicle received during the war. Engineers from Volkswagen, Daimler-Benz, and Auto Union examined every aspect of the Jeep's design and construction. The cooling system received particular attention given the field reports from North Africa, describing performance that contradicted German engineering doctrine. Dr. Ferdinand Porsche himself, designer of the Kübelwagen, spent several hours examining a captured Jeep in February 1943. His conclusions, recorded in a memorandum to the Army Weapons Office, acknowledged the American cooling system's effectiveness while defending his decision to use air cooling in the Kübelwagen. The American water cooling system demonstrates considerable engineering merit for high-power applications in extreme conditions. Their willingness to accept additional weight and complexity achieves thermal management capacity that air cooling cannot match at comparable power levels. However, the Kübelwagen's lower power output and lighter weight remain appropriate for its intended reconnaissance role. Each approach represents valid engineering choices optimized for different requirements. This measured assessment from Germany's most respected automotive engineer indicated how thoroughly the Jeep's performance had challenged German assumptions. Porsche, who had championed air cooling based on sound engineering principles, now acknowledged that American water cooling had proven superior under specific conditions. The comprehensive German testing revealed specifications that Wehrmacht planners found sobering. The Jeep's cooling system maintained stable operating temperatures under conditions that would destroy the Kübelwagen's air-cooled engine. In sustained maximum power operation, the Jeep's engine temperature stabilized at approximately 82 degrees Celsius and remained there indefinitely. The Kübelwagen's cylinder head temperatures under similar loads exceeded 150 degrees Celsius, approaching limits where engine damage became likely. The Jeep could operate continuously at maximum power for hours without overheating. The Kübelwagen required periodic cooling stops during sustained high-load operation to prevent engine damage. The Jeep's cooling system tolerated significant coolant loss without immediate failure. The surge tank's capacity and the generous cooling margins meant the engine could operate with coolant levels below optimal for extended periods. The Kübelwagen's air cooling provided no similar tolerance. Once cylinder head temperatures exceeded safe limits, engine damage was rapid and often catastrophic. German test drivers reported that the Jeep felt more powerful and responsive than the Kübelwagen, particularly under desert conditions. The 60-horsepower Go Devil engine, operating at stable temperatures under its water cooling system, delivered consistent power output regardless of ambient conditions or operating duration. The Kübelwagen's 25-horsepower engine, operating near thermal limits under heavy loads, experienced power loss as temperatures climbed and oil viscosity decreased. Hauptmann-Weber's final technical report, submitted in March 1943, contained an assessment that must have been painful for a German engineer to write. We must acknowledge that American cooling system engineering has achieved results superior to our own approach for high-power applications in extreme thermal environments. The water cooling system we dismissed as vulnerable and unsuitable for desert operations has proven more reliable and capable than our air-cooled designs. This represents not a failure of German engineering principles, but a failure to recognize that different operating conditions require different solutions. The Americans designed their cooling system for the real conditions their vehicles would face, accepting weight and complexity penalties to achieve reliability margins. We designed for theoretical optimization, creating systems that excel under ideal conditions, but lack robustness under harsh realities. Under combat conditions in North Africa, reliability margins prove more valuable than theoretical efficiency. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Jeep's cooling system reliability had strategic implications beyond individual vehicle performance. German logistics in North Africa struggled constantly with engine failures and vehicle breakdowns. Every Kübelwagen engine seized from thermal overload removed a vehicle from service, often for weeks or months, while replacement engines were located and shipped from Germany. Every German vehicle that required frequent cooling stops during operations reduced overall unit mobility. Every maintenance hour spent repairing heat-damaged engines consumed scarce technical expertise. By contrast, American Jeeps simply kept running. Their generous cooling margins and robust designs meant vehicles required minimal maintenance, even under brutal operating conditions. When maintenance was needed, simple, robust components could be repaired or replaced quickly using basic tools. The strategic advantage this conferred on Allied forces was profound. German intelligence services attempted to determine American cooling system production capacity and costs. What they learned was as disturbing as the technical performance data. The radiators, water pumps, thermostats, hoses, and other cooling system components were mass-produced using manufacturing techniques that kept costs low while maintaining quality. Willys Overland and Ford together operated production lines that could build complete Jeeps, including their sophisticated cooling systems, at rates exceeding 500 per day by mid-1943. The cooling system added only about $35 to each Jeep's manufacturing cost. This represented remarkable efficiency. German cooling system components, whether for air-cooled or water-cooled engines, required more machining, more hand-fitting, and more skilled labor. The result was higher costs, slower production, and lower output. Oberst Hartmann, promoted and transferred to training duties in Germany after recovering from wounds received in North Africa, reviewed captured intelligence reports in late 1943. His diary entry that evening reflected on implications that extended beyond technical specifications. We face an enemy who can mass-produce vehicles with cooling systems that outperform our own designs. Our ideology insists Americans are inferior engineers, yet their Jeeps function flawlessly in conditions that destroy our vehicles. Our propaganda claims American industry emphasizes quantity over quality, yet they produce cooling systems superior to ours at lower cost in quantities we cannot match. The Jeep's radiator alone represents a level of manufacturing sophistication we struggle to equal. The cooling system's superiority became particularly apparent during summer months in North Africa, when ambient temperatures regularly exceeded 45 degrees Celsius. Under these conditions, the Kübelwagen's air cooling reached its limits. Cylinder head temperatures climbed dangerously high even during moderate load operation. Prolonged high-load operation became impossible without engine damage. German units learned to conduct operations during cooler morning and evening hours, avoiding midday heat that would destroy their vehicles' engines. American forces faced no such constraints. Jeeps operated continuously, regardless of ambient temperature. Their cooling systems maintained stable engine temperatures in midday heat that made metal surfaces painful to touch. This thermal immunity gave American units operational flexibility German commanders could not match. Attacks could be launched during the hottest hours when German mobility was constrained. Reconnaissance could continue throughout the day while German vehicles sat cooling their engines. Supply convoys could maintain schedules that German logistics could not duplicate. General Major Ludwig Cruel, who commanded German forces during portions of the North African campaign, noted in post-war interviews that American vehicle reliability influenced tactical planning. We knew American Jeeps could operate in conditions that would destroy our Kübelwagens. This meant American reconnaissance units could maintain contact with our forces continuously, while our reconnaissance was intermittent. American supply columns could move during hours when our vehicles required cooling stops. American commanders enjoyed operational tempo advantages derived from simple mechanical superiority. We could destroy American vehicles in combat, but their cooling system reliability meant they retained mobility advantages we could not overcome. This assessment from a senior German commander illustrated how mechanical engineering details translated into strategic consequences. By spring 1943, German technical intelligence had assembled comprehensive documentation of the Jeep's cooling system design and performance. This information was distributed to German automotive manufacturers, with instructions to develop improved cooling systems for military vehicles. The results demonstrated how difficult it was to replicate American engineering approaches within German manufacturing constraints. Daimler-Benz engineers attempted to design an improved water cooling system for a proposed light reconnaissance vehicle. Their system incorporated a surge tank similar to the Jeep's design, a larger radiator with wider fin spacing, and a robust water pump based on American principles. The resulting system would have performed well, but costs were prohibitive. The radiator alone would cost approximately 3 times what the Jeep's radiator cost to manufacture. Production tooling requirements exceeded available capacity. The complete cooling system would add substantially to vehicle weight and cost. The project was abandoned. Volkswagen engineers evaluated modifications to improve the Kübelwagen's air cooling performance under high thermal loads. They experimented with improved cooling fin designs, higher capacity cooling fans, and supplemental oil cooling systems. Modest improvements were achieved, but fundamental limitations remained. Air cooling simply could not dissipate the heat generated by sustained high-power operation in desert temperatures. Without moving to water cooling, which would require complete vehicle redesign, significant improvement was impossible. The German attempts to replicate or improve upon American cooling system engineering illustrated a painful reality. The Jeep's cooling system superiority derived not from any single brilliant innovation, but from a comprehensive engineering approach that emphasized reliability margins, robust components, and manufacturing efficiency. Replicating this approach required not just copying specific components, but transforming entire design and manufacturing philosophies. German engineering culture emphasized theoretical optimization and precision manufacturing. American engineering culture emphasized practical robustness and production efficiency. The Jeep's cooling system represented the product of that American engineering culture, and it could not be duplicated simply by copying individual components. By 1944, with Germany on the defensive across all fronts, captured Jeeps became prized possessions among German units. Standing orders required captured vehicles be sent to rear areas for evaluation, but commanders routinely ignored these directives. A Jeep that could operate reliably in any conditions was too valuable to surrender. German maintenance personnel learned to keep captured Jeeps running despite parts supply challenges. They fabricated replacement hoses, repaired radiators using available materials, and improvised fixes for cooling system problems using whatever resources they could scrounge. The fact that German mechanics were willing to invest scarce time and materials, maintaining captured American vehicles, rather than keeping German equipment operational, spoke to the Jeep's superiority. Feldwebel Hans Becker, who managed vehicle maintenance for a Panzer Grenadier regiment in Italy, kept detailed logs of vehicle reliability. His records showed captured Jeeps required approximately 30% less maintenance time than Kübelwagens. Most significantly, Jeeps experienced virtually no cooling system failures, while Kübelwagens suffered frequent heat-related engine problems requiring major repairs. When given the choice between maintaining a captured Jeep or a German Kübelwagen, Becker's mechanics consistently chose to work on the Jeep, knowing it would remain operational longer and require less intervention. The post-war technical analysis of Allied equipment conducted by former Wehrmacht officers working for American military intelligence rated the Jeep as one of the 5 most significant pieces of equipment in the Allied victory. The assessment noted that the Jeep's cooling system reliability contributed substantially to its effectiveness. A vehicle that requires minimal maintenance and functions reliably under extreme conditions multiplies its value many times over. The Jeep's cooling system provided this reliability, enabling operational tempo and logistical efficiency German forces could not match. General Dwight Eisenhower wrote in his memoirs that senior Allied officers regarded the Jeep as one of the 5 pieces of equipment most vital to success in Europe and North Africa. While Eisenhower didn't specifically cite the cooling system, Wehrmacht officers who captured and operated Jeeps understood that cooling system reliability was fundamental to the vehicle's overall effectiveness. A vehicle with excellent mobility but unreliable cooling would have been nearly useless in North African conditions. The cooling system's superiority made all the Jeep's other advantages practical and sustainable. Hauptmann Weber, whose initial examination of a captured Jeep in June 1942 began the Wehrmacht's technical evaluation of American cooling systems, survived the war and immigrated to the United States in 1951. In a 1968 interview for an automotive history project, he reflected on his wartime experiences examining American engineering. The Jeep's cooling system taught me that engineering excellence is not about theoretical sophistication but practical effectiveness. German engineering pursued optimization, seeking the most elegant solution to clearly defined problems. American engineering pursued robustness, seeking solutions that would function reliably under conditions that exceeded specifications. In the laboratory, German approaches often produced superior results. On the battlefield, American approaches proved more successful. The Jeep's cooling system seemed crude to German engineers accustomed to precision optimization. It was oversized, heavy, and incorporated what we considered unnecessary components like the surge tank, yet it functioned flawlessly under conditions that destroyed our more elegant air-cooled designs. This was a profound lesson about the difference between theoretical excellence and practical superiority. Germany produced approximately 50,000 Kübelwagens during the entire war. The United States produced over 640,000 Jeeps. This 12-to-1 production advantage represented only part of the disparity. American Jeeps also served with British, Canadian, Australian, Free French, Soviet, and Chinese forces under Lend-Lease. Some 50,000 went to the Soviet Union alone, more than Germany's total Kübelwagen production. Every one of those Jeeps carried a cooling system that demonstrated American engineering superiority over German equivalents. Every German soldier who encountered American forces saw vehicles that could operate reliably in conditions that destroyed German equipment. The psychological impact of this mechanical superiority extended far beyond simple vehicle counts. Oberleutnant Hans Richter, who served in North Africa and later Italy, described the demoralization of watching American vehicles function effortlessly while German equipment failed. We knew we were fighting an enemy with superior industrial capacity, but seeing their Jeeps operate hour after hour in heat that destroyed our engines, watching them maintain operational tempo while we waited for our vehicles to cool, observing their maintenance crews spend minutes on simple repairs that took us hours, this demonstrated technological superiority that undermined confidence. We could fight bravely and skillfully, but we were using inferior tools against an enemy whose engineering excellence matched their industrial might. The captured Jeep, examined by Wehrmacht mechanics in North Africa, began as a technical curiosity, another piece of captured enemy equipment to be evaluated and understood. It became a symbol of American engineering approaches that German technical doctrine could not match. Sophisticated German air cooling design meant nothing when simpler American water cooling proved more reliable under combat conditions. Ideological certainty about American technical inferiority meant nothing when American cooling systems outperformed German equivalents in direct comparison. The comprehensive German technical evaluation of the Jeep's cooling system, conducted by competent engineers trained in German technical universities, documented capabilities that contradicted propaganda. The reports German officers like Weber, Hartmann, Steinmetz, and Kruger wrote established that American cooling system engineering had achieved remarkable results through methods different from German practice. In the final analysis, the story of Wehrmacht mechanics examining the Jeep's cooling system documents one of the most significant technical assessments of the war. Competent engineers trained in German technical tradition examined an American vehicle and recognized excellence. Their honest technical assessments, documented in reports that survived the war, provide unique insight into the moment when German military professionals recognized the truth. They faced an enemy whose cooling system, engineering, and by extension whose broader industrial and technical capabilities exceeded their own. The Jeep's radiator was proof they could touch, test, and measure, a simple mechanical system that represented a vast truth about the war they were losing. The cooling system's legacy extended into post-war vehicle design. Soviet engineers who examined Lend-Lease Jeeps under the Red Army's technical evaluation programs paid particular attention to the cooling system. The GAZ-67, introduced in 1943 as the Soviet military's standard light vehicle, incorporated cooling system features clearly influenced by American Jeep design. The radiator employed wider fin spacing than pre-war Soviet practice, reducing sand accumulation problems. A surge tank was added to handle thermal expansion, a feature absent from earlier Soviet cooling systems. Water pump designs emphasized robust construction over theoretical efficiency, following American precedent. These modifications represented the Soviet Union's acknowledgement that American cooling system engineering had achieved practical advantages worth copying. British military planners conducting their own evaluation of captured jeeps in North Africa reached similar conclusions about cooling system superiority. Technical reports prepared by Royal Army Service Corps engineers in late 1942 noted that British military vehicles employing water cooling experienced overheating problems under desert conditions, while American jeeps operated without such difficulties. The British reports attributed this disparity to American willingness to accept weight penalties for cooling system capacity margins. British cooling systems were optimized for European operating conditions. American systems were designed for worst-case scenarios, including sustained operation in extreme heat. The result was British vehicles that performed adequately under normal conditions but struggled under thermal stress, versus American vehicles that maintained consistent performance across all conditions. This assessment influenced post-war British military vehicle design, with specifications requiring cooling system capacity substantially exceeding calculated minimums. French forces operating under American command in North Africa and Italy provided additional documentation of Jeep cooling system reliability. General Jean de Lattre de Tassigny, commanding French forces in Italy during 1944, noted in his operational reports that American Jeeps issued to French units maintained exceptional reliability despite poor maintenance conditions. French mechanics, accustomed to temperamental French military vehicles requiring constant attention, found the Jeeps remarkably tolerant of neglect. Oil changes performed irregularly, coolant levels checked infrequently, and maintenance procedures ignored still resulted in functional vehicles. The cooling systems in particular seemed designed to function despite abuse. Radiators tolerated significant coolant contamination without failure. Water pumps continued operating with worn bearings that would have destroyed French equivalents. Thermostats functioned properly even when coolant chemistry was completely wrong. This forgiveness of poor maintenance practices reflected American engineering philosophy, emphasizing robust designs that functioned under non-ideal conditions rather than optimized designs requiring perfect maintenance. The psychological impact on German soldiers of watching American vehicles operate effortlessly in conditions that destroyed German equipment cannot be overstated. Every Wehrmacht soldier who served in North Africa witnessed the disparity. German vehicles required cooling stops during extended operations. American vehicles did not. German engines seized from thermal overload. American engines kept running. German units planned operations around their vehicles' thermal limitations. American units faced no such constraints. This daily demonstration of mechanical inferiority affected morale in ways difficult to quantify but impossible to ignore. Gefreiter Wilhelm Schmidt, who served as a mechanic in North Africa from 1942 through 1943, wrote in his diary about the psychological weight of maintaining German vehicles that could not match American capabilities. "We work constantly to keep our Kubelwagens operational, while captured American Jeeps sit idle for days, then start immediately and run flawlessly. The Americans built better vehicles. We tell ourselves German engineering is superior, but the evidence before us says otherwise. Every seized engine, every overheated vehicle, every cooling stop reminds us we are fighting with inferior equipment. This demoralization is as real as any combat casualty. The strategic implications of cooling system reliability extended beyond individual vehicle performance. German logistics planners attempting to move supplies and reinforcements across North Africa's vast distances found themselves constrained by their vehicles' thermal limitations. Operations had to be planned around cooling requirements. Convoys required extended travel times to accommodate cooling stops. Critical movements during hot daylight hours risked vehicle losses from overheating. American logistics faced no such constraints. Convoys moved continuously regardless of temperature. Operations could be scheduled without considering thermal stress on vehicles. Supply lines functioned with predictable efficiency because vehicles maintained consistent performance under all conditions. This logistical advantage multiplied force effectiveness. German units might possess adequate supplies, but those supplies moved slowly and unpredictably. American units received supplies quickly and reliably because the vehicles delivering them functioned without thermal constraints. General Erwin Rommel, commanding German forces in North Africa, noted the vehicle reliability disparity in his communications with Berlin. His requests for increased vehicle allocations cited not just combat losses, but mechanical attrition from desert conditions that German vehicles could not withstand. American vehicles captured and pressed into German service demonstrated the problem clearly. They operated reliably in conditions destroying German equipment. Rommel's assessment was unambiguous. We require vehicles designed for desert conditions, not vehicles optimized for European use. The Americans understood this and designed accordingly. We did not, and the result is mechanical attrition that compounds our numerical disadvantages. His superiors in Berlin could not address this problem. Germany lacked the industrial capacity to design, test, and produce new vehicles while simultaneously maintaining existing production. The cooling system engineering that would have solved the problem required time, resources, and manufacturing capability Germany no longer possessed. By war's end, the Jeep's cooling system had become a case study in effective engineering approach. American engineers had designed for real-world conditions rather than theoretical optimization. They accepted weight and complexity penalties to achieve reliability margins. They emphasized robust components over precision optimization. They created systems tolerant of poor maintenance and harsh conditions. The result was cooling systems that functioned effectively across environments ranging from Arctic to desert, under operating conditions ranging from careful maintenance to complete neglect. German engineers, trained in theoretical optimization and precision manufacturing, had created cooling systems that excelled under ideal conditions but failed under harsh realities. The comparison was definitive. Practical robustness proved more valuable than theoretical elegance. Hauptmann Weber, reflecting decades after the war, summarized the lesson the Jeep's cooling system taught German engineers. We approached engineering as an academic exercise in optimization. The Americans approached it as a practical challenge in reliability. Our systems were beautiful on paper, elegant in execution, and fragile in practice. Their systems were crude by our standards, overbuilt by our calculations, and utterly reliable in reality. The war taught us that engineering excellence is measured not by theoretical sophistication, but by practical performance under the worst conditions users will encounter. The Jeep's cooling system embodied that philosophy. It was not the most elegant design, not the most efficient, not the lightest or most compact. It was simply the most effective at accomplishing its mission under real-world conditions. That made it superior to our alternatives, and that superiority helped determine the war's outcome. Small engineering decisions, multiplied across hundreds of thousands of vehicles, accumulated into strategic advantages we could not overcome. The final verdict on the Jeep's cooling system came not from engineers or generals, but from the soldiers who depended on these vehicles daily. American soldiers trusted their Jeeps completely, knowing the vehicles would function reliably regardless of conditions. German soldiers who captured Jeeps fought to keep them, recognizing their superiority over German equivalents. British, French, Soviet, and other Allied soldiers who received Jeeps under Lend-Lease appreciated their reliability. This universal recognition from the vehicle's actual users provided the most authoritative assessment possible. The Jeep's cooling system, unremarkable in appearance and simple in principle, represented engineering excellence measured by the only standard that truly mattered. It worked, consistently and reliably, under conditions that destroyed alternatives. That practical superiority, repeated across more than 640,000 vehicles operating on every front in World War II, made it one of the most significant technical achievements of the conflict. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.